Great. All right. Hello, everyone. I'm Nicklas, and it's great to be here. In this short presentation, I would like to introduce our very recent work on deep Q-learning under data augmentation. And this is joint work together with Hansen and Xiaolong Wang. So data augmentation is a promising technique for improving the generalization in RL. And it generally holds the promise of enabling the use of RL in much broader contexts than today. However, learning a policy without augmentation is already pretty difficult. So with increasingly much use of data augmentation, the optimization problem that we are trying to solve also becomes a lot more challenging. And to demonstrate this problem, we here show learning curves of DRQ, which is a recent method for image-based RL. Here we train policies and tasks from the DeepMind control suite, and each of the curves here correspond to one of 6 common choices of data augmentation. And we generally observe that the performance of DRQ is very dependent on the choice of the data augmentation, and also that the different augmentations affect each task differently. So in this work, we propose SVIA, which is a method for stabilizing the deep Q-learning algorithms under use of data augmentation. And compared to DRQ, our method is relatively unaffected by the choice of the data augmentation. In this work, we identified 2 major causes of instability when using data augmentation. First, non-deterministic Q targets, which is mostly due to the stochastic nature of data augmentation. And second, what we call an over-regularization effect, where the augmented data dominates the gradient and prevents convergence. Our method makes the following changes compared to previous work. Given an observation ST, we apply data augmentation to produce an augmented observation. And we then optimize the Q function over both the augmented and the non-augmented samples by simply concatenating along the batch dimension. And to reduce the target variance, we compute Q targets strictly from the unaugmented data. And if the base algorithm also learns an actor, then we optimize it strictly from unaugmented data as well. And we instead learn generalizable policy through implicit parameter sharing. We further investigate the stability of generalization of RL algorithms using vision transformers. The blue curve shown here is DRQ trained without augmentation. The orange curve is then DRQ trained with augmentation. And the red curve is our method using the same choice of data augmentation. And we find that while DRQ using vision transformers is very unstable when trained on augmented data, the sample efficiency of our method is virtually unaffected. And when we evaluate the generalization to unseen environments, we find that vision transformers overfit significantly without use of data augmentation. Our method greatly improves the generalization without decreasing the sample efficiency. And we therefore think it could be a key component in future research on more large-scale RL. So using strong data augmentation, our method is able to generalize to a wide variety of unseen environments with different distribution shifts, even when we only train it with a fixed environment, which is shown to the left. We evaluate our method on a total of 6 tasks from the DeepMind control suite, as well as 3 robotic manipulation tasks shown here. For more information about our work, please check out the link here, which contains our paper as well as implementations of our method, our baselines, and all of our test environments. Thank you.
Thank you, Nicklas. And any questions from the audience?
I have a quick question. Could you specify more about what's the type of data augmentation are you using? I see like lighting or background. What else do you do?
So the 6 augmentations that we use are common data augmentations from computer vision. Let me see. So we use a random convolution, which is from previous work on generalization and RL. Then we use like a Gaussian blur, and we use cutout and a random overlay augmentation, and then like random rotation, and also like a color jitter and these kind of augmentations as well.
Thank you.
And so of course the generalization that you get is by using these augmentations also depend on where you're deploying your agent, right? So some data augmentations are more effective at generalizing to certain kinds of distribution shifts, but we are just evaluating the stability in general. Good question.
Yes.
Yeah.
Yeah, thank you. And do you combine these augmentation together to train your network, or just test one by one?
Yes, in this work, we just evaluate them individually and see which augmentations are most problematic in terms of stability.
Okay.
And but in general, it turns out in our experiments that the ones that are hardest to optimize are also the ones that have the biggest benefits in generalization, at least in our distribution shifts.
Yeah, thank you.